Welcome to another deep dive. Today, we're taking a trip to the edge of the periodic table, exploring the strange world of Nihonium, an element so elusive it practically disappears right after it's made. You wanted to learn more about Nihonium, and let me tell you, getting up to speed on this topic was mind-blowing, even for me. It's a story of atomic hide-and-seek, with scientists acting as detectives, chasing these fleeting atoms and piecing together clues from their radioactive decay.
What's so captivating about nihonium is that it's a synthetic element. It doesn't exist naturally anywhere on Earth. Scientists have to create it in a lab, atom by atom, and they only have fractions of a second to study it before it decays into something else.
I'm already picturing scientists huddled around monitors, watching these tiny atomic fireworks. But before we get into the nitty-gritty of the discovery, I have to ask, how do you even begin to make an element? It sounds like something out of science fiction.
It all starts with nuclear fusion. Think of it like forcing two magnets together, the ones that repel each other. You need an incredible amount of energy to overcome that repulsion and get them to fuse. In this case, we're talking about smashing atomic nuclei together, the very hearts of atoms.
Okay, so we're talking about massive particle accelerators, right? Like those behemoths you see in documentaries, smashing atoms together at nearly the speed of light.
That's one way to do it. And there are a couple of approaches to this atomic smash-up. There's hot fusion, where you slam a lighter element into a heavier one at extremely high speeds. This creates a super excited, very unstable nucleus. It's like a hot potato that wants to cool down by shedding energy and particles.
And that's where the decay chain comes in, right? It's like a trail of breadcrumbs leading back to the original element. But you mentioned another approach, cold fusion. What's the difference?
Good point. And yes, the decay chain is key to identifying these fleeting elements. With cold fusion, we use heavier projectiles and later targets. This leads to less excited, slightly longer-lived nuclei, but they're still incredibly unstable.
So it seems like scientists are walking this tightrope between creating an element and making sure it doesn't vanish. Before they can even get a good look at it, what makes nihonium such a challenge to create?
Well, the challenge with super heavy elements like nihonium is that the more protons you pack into a nucleus, the more unstable it becomes. It's like trying to build a tower with blocks that keep repelling each other.
Yeah.
You need the right building blocks and a very delicate touch.
And this is where calcium-48 comes into play, right?
Yeah.
I read that this particular isotope of calcium is a bit of a secret weapon in the world of element creation.
Exactly. Calcium-48 is what physicists call doubly magic. This means it has a special combination of protons and neutrons. That makes its nucleus incredibly stable. When you use calcium-48 as a projectile in fusion reactions, some of that stability can actually transfer to the newly formed super heavy element.
It's like calcium-48 is donating some of its stability, giving the new element a fighting chance, even if it's just for a fleeting moment. That's brilliant.
It is. Think of it like a skilled architect who knows just the right way to support a delicate structure. In the case of nihonium, calcium-48 helps to prop up that unstable nucleus, giving scientists those precious few milliseconds to observe it.
This is already shaping up to be a fascinating detective story. So tell me, who are the key players in this scientific race? To create and identify nihonium, was it a single team, or were there multiple groups hot on the trail?
Actually, the story of nihonium involves a bit of a scientific showdown. It starts with early attempts to create super heavy elements using cold fusion, but they had limited success. Then, in the 1970s, a team at the Joint Institute for Nuclear Research, or JINR, in the Soviet Union, decided to switch gears to hot fusion, and they chose calcium-48 as their projectile of choice.
So they were the first to successfully create nihonium.
Well, it's a bit complicated. In 1998, they may have accidentally created nihonium-290 as a byproduct of another experiment, but the results were debated. It sparked a race between two teams. The JINR, now in collaboration with Lawrence Livermore National Laboratory in the U.S., and a team at Riken in Japan, each using a different approach.
Okay, so we have a transcontinental rivalry brewing. Tell me more about these teams and their methods.
The JINR-LNL team, sticking with their hot fusion approach, claimed in 2003 to have created element 115, which then decayed into nihonium. They bombarded americium-243 with those trusty calcium-48 projectiles. Meanwhile, the Riken team, led by Kosuke Morita, took a different route. They used cold fusion with bismuth-209 and zinc-70, hoping for a more easily identifiable decay chain.
So, two different approaches, both aiming for the same elusive target. It sounds like a nail-biter. But before we delve into who ultimately won this scientific showdown, I'm curious, how do you actually prove you've created a new element? What are the rules of the game in this atomic competition?
That's a great question. In the world of element discovery, It's not enough to just create something new. You need to prove it beyond a shadow of a doubt. And that's where the Joint Working Party, or JWP, comes in.
The JWP. Sounds serious.
They are. The JWP is like the scientific referee. For new element discoveries, they're a collaboration between two international organizations, IUPAC and IUPAP. And they have very strict criteria for validating a claim. It's like presenting your case in a scientific court.
So what kind of evidence do these atomic detectives need to present to the JWP? What's the burden of proof for a brand new element?
First, the element must have a different atomic number than any known element. That's the number of protons in its nucleus, which defines what element it is. Then they have to show that its properties, either physical or chemical, are distinct and don't match any previously known element.
That makes sense. You can't just say, oh, it looks shiny, so it must be new. But with Nihonium decaying so quickly, how do they even have time to measure its properties?
That's the real challenge. Most of what we know about Nihonium's properties is based on theoretical calculations. But the key to proving its existence lies in its decay chain. The JWP requires something called cross-reactions and anchoring. Think of it like connecting the dots.
Okay, I'm intrigued. Walk me through this connect the dots process. What are cross-reactions and anchoring, and how do they apply to Nihonium?
Cross-reactions involve creating the same element using different nuclear reactions. So if both the JINR LLNL team and the Riken team could create Nihonium using different methods, it would strengthen the evidence. Anchoring is even more crucial. It means demonstrating that the decay chain of the new element ultimately leads to a known, stable isotope. It's like tracing a family tree back to a well-documented ancestor.
So they're not just observing Nihonium in isolation, they're watching it transform and making sure it aligns with the known family tree of elements. It's like a radioactive puzzle.
Exactly. And in the case of Nihonium, both teams face the challenge of creating enough atoms, observing those fleeting decay chains, and convincing the JWP that their data was solid.
So, after all that, who emerged victorious? Did either team manage to satisfy these rigorous criteria and claim the title of Nihonium Discoverer?
It was a long and winding road, with both teams presenting their findings, facing scrutiny from the JWP. And going back to refine their experiments, the JINR LLNL team focused on bolstering their claim with chemical studies on dubnium, a decay product of element 115, which they said proved their method created Nihonium.
So, they were trying to solidify their argument by showing that the decay products matched expectations. Clever. But what about the Riken team? What was their strategy?
The Riken team took a slightly different approach. They focused on creating more atoms of Nihonium-278, the isotope they produced using cold fusion, and they succeeded in observing a longer decay chain, which ultimately anchored it to Mendelevium-254, a known and well-characterized isotope.
So they found that crucial link to a known ancestor in the element family tree. It sounds like a meticulous and incredibly challenging process. But did the JWP finally declare a winner in this scientific marathon?
Yes. In December 2015, after years of back and forth, the JWP finally awarded credit for the discovery of Nihonium to the Riken team. Their approach, coupled with the observation of that longer decay chain, ultimately tipped the scales in their favor.
That's quite a victory. So the Riken team got to choose the name, right? I'm guessing they went with something that reflected their hard work and dedication. Maybe Rikenium to commemorate the institute where the discovery was made.
While Rikenium might have been a fitting tribute to their hard work, they chose a name with a deeper meaning. They named it Nihonium, derived from Nihon, one of the Japanese words for Japan.
Nihonium. It has a nice ring to it. And I imagine it must have been a proud moment for Japan to have an element named after their country.
Absolutely. It's a testament to their scientific prowess and a recognition of the years of dedicated effort by the Riken team. But the story doesn't end there. The name Nihonium also carries a special historical significance, connecting it to another Japanese scientist who, almost a century earlier, came tantalizingly close to discovering a new element.
Oh, tell me more. I love these little twists and turns in the history of science.
Back in 1908, a Japanese chemist named Masataka Ogawa claimed to have discovered element 43, which he named Nihonium after another pronunciation of Japan. He even presented his findings at the prestigious British Chemical Society.
So, he was on the verge of making history. What happened? Why isn't Nihonium on the periodic table?
Unfortunately. Later analysis revealed that Ogawa had actually discovered a mixture of elements, not a new one. Element 43 was eventually discovered in 1937 and named technetium.
So Nihonium is a way to honor Ogawa's efforts and finally give Japan a well-deserved spot on the periodic table. It's a beautiful tribute to the enduring legacy of scientific exploration, even when the initial claims don't quite pan out. But let's zoom back in on Nihonium itself. What do we actually know about this elusive element? What's it like? What are its properties?
Well,
Hmm.
that's the fascinating and frustrating thing about Nihonium. Because it decays so rapidly, we know very little about its actual properties. Most of what we understand is based on its position on the periodic table and theoretical calculations.
It's like a puddle with only a few pieces filled in. Let's try to piece together what we know, or at least what scientists predict. About Nihonium, based on where it sits in the periodic table, what clues does its position give us?
Nihonium sits below thallium in group 13 of the periodic table. Based on this, it's predicted to be a metal. But it might be less reactive than thallium. Some even think it could be a noble metal like gold or platinum, meaning it's resistant to corrosion and doesn't readily react with other elements.
A noble metal. That's intriguing. So we might have a microscopic, incredibly radioactive speck of potential precious metal.
It's certainly a possibility, and because of something called relativistic effects, which become more prominent in heavier elements, Nihonium is also predicted to be denser than thallium.
Hold on. Relativistic effects. You're going to have to explain that one. It sounds like something out of Einstein's playbook.
It does, essentially. The electrons in heavier elements are moving so fast, close to the speed of light, that their behavior is affected by Einstein's theory of relativity.
Wow. So these super speedy electrons in Nihonium could actually be making it denser. That's mind-blowing.
It is, and it highlights how exploring the far reaches of the periodic table takes us to the very edge of our understanding of physics and chemistry. Another prediction about Nihonium, based on its position in group 13, is that it's more stable in the +1 oxidation state compared to +3.
Okay. You've lost me a bit there. What does oxidation state mean, and why is that significant?
Think of it like this. Elements like to share electrons to form chemical bonds. The oxidation state tells us how many electrons an atom is willing to share, or give up. In the case of Nihonium, it's predicted to be more stable when it shares just 1 electron, as opposed to 3.
So, it's a bit of a lone wolf, preferring to keep most of its electrons to itself. I'm starting to get a picture of this elusive element, potentially a noble metal, denser than its lighter relative, a bit stingy with its electrons. But all this is based on predictions, right? Have there been any attempts to actually study Nihonium in the lab?
There have been some incredible, almost mind-bogglingly difficult experiments done, mostly at JINR. To try and tease out some of Nihonium's properties, they focused on understanding how it behaves chemically, specifically its volatility and adsorption behavior.
All right, I'm all ears. Break down those terms for me. What do volatility and absorption mean in this context?
Volatility refers to how easily a substance turns into a gas. So, for example, oxygen is very volatile. It exists as a gas at room temperature. Gold, on the other hand, is not very volatile at all. Adsorption is about how a substance sticks to surfaces, some elements, like those sticky gecko feet, adhere very strongly, while others barely interact with surfaces.
So, they're trying to figure out if Nihonium is more of a floater, easily turning into a gas, or if it prefers to cling to surfaces. What techniques are they using to study this?
They've used a technique called thermochromatography. It involves creating a temperature gradient along a surface and then introducing Nihonium atoms to see where they prefer to stick. The idea is that different elements will have different sticking points based on their volatility and chemical properties.
That's ingenious. So what have they learned so far? Does Nihonium float like a butterfly? Or cling like a gecko?
Well, the early results are fascinating. They suggest that Nihonium might not be as volatile as some of the super heavy elements in the noble gas group. It might actually be less reactive than its lighter relative, thallium, which is surprising.
So it might be less of a floater and more of a clinger. That goes against expectations, doesn't it?
It does. But remember, these experiments are incredibly challenging, and we're only just beginning to scratch the surface of Nihonium's behavior. To really understand this element, we need to create more of it. And more importantly, we need longer-lived isotopes.
Which brings us back to the island of stability earlier. You mentioned this theoretical region of the periodic table where super heavy elements with much longer half-lives might exist. How does Nihonium fit into this quest for the island?
Nihonium is like a signpost pointing toward the island. As we create heavier and heavier isotopes of Nihonium, their half-lives actually increase, suggesting that we might be approaching the shores of this elusive island.
So each new Nihonium isotope is like a step closer to this scientific El Dorado. What's the most stable isotope they've discovered so far?
The current record holder is Nihonium 286, with a half-life of 8 seconds. It's still a far cry from the millions of years predicted for the heart of the island, but it's a promising sign that we're on the right track.
8 seconds. It's amazing to think that scientists can do any experiments at all with something that exists for such a short time. What would it mean for science if we were to actually reach the island of stability? What could we learn?
Reaching the island of stability would be a monumental achievement. It would not only confirm our theoretical understanding of nuclear physics, but also open up a whole new world of possibilities for scientific exploration. Imagine being able to study super heavy elements that last for years, or even centuries. We could delve into their chemical properties, explore potential applications in material science and technology, even test the very limits of the periodic table.
It's almost like discovering a new continent on the periodic table. But even if we never find this mythical island, the pursuit of nihonium and other super heavy elements has already taught us so much about the fundamental nature of matter. It's a testament to human ingenuity and our insatiable curiosity.
It is the story of Nihonium, from those high-energy collisions that create these fleeting atoms, to those meticulous experiments designed to catch a glimpse of their properties, is a reminder that science is a journey of discovery, and the pursuit of knowledge is often its own reward.
And who knows what other scientific treasures might be lurking in the depths of the periodic table. Maybe one day. We'll be doing a deep dive into an element with a half-life of 1,000,000 years, thanks to the trailblazing work done with elements like nihonium.
That's the beauty of science. There's always something new to explore, and each discovery opens up more questions than answers, driving us to delve even deeper into the mysteries of the universe.
Well said. This deep dive into the world of nihonium has been an incredible journey, and I want to thank you for being such an insightful guide. It's left me with a sense of awe and a renewed appreciation for the scientists who are pushing the boundaries of what we know.
It's been my pleasure. And remember, the pursuit of knowledge is a never-ending adventure, so keep exploring, keep asking questions, and who knows what you might discover.